we talked about quadratics as functions that are written in y equals ax squared plus bx plus c. Another way of being written is instead of y equals, you could say f parentheses x is equal to. Remember, kind of like linear. So with that, there's a couple of things that you all identified about quadratics. You said that you could tell by looking at a graph if it is a quadratic, if it does what? If it forms a parabola, which we said power of 2 makes a u. So the two different ways that you could show visually, the two different ways that you can see that something is a quadratic is if it has a power of 2 as the highest exponent, and if it's a graph, if it makes a U shape. However, there are some other ways that you could tell if something is a quadratic if you're not given the equation nor the actual graph. This way is kind of like when we did constant rate of change with y equals mx plus b. You remember you would have a table of values and you would have numbers written and you would look to see if there was a change of y over change of x that was the same. That's how we found linear functionality. Well, quadratic functionality is found, and I'm going to skip through this a little bit, if you have what we call second differences. So if you're looking at this here, let's just look at the table, which you see is written up there. This table, if I asked you, hey, is this a quadratic? As it stands right now, you would probably think, well, the only way I can do this is if I graph it and make a U shape, if it makes a U. However, because of the fact that it's a power of 2, you could look to see if it's a quadratic by checking if there's a constant rate of x value change and a double difference in the y value. Double difference y. Think of double difference as power of 2 for y. So if you're looking at this table of values, you're going to notice that you go from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. The x is constant. That's good. Now you go to the y's. And when you look at the y values, you're going to go from 0 to 1, you went up by 1. 1 to 4, you went up by 3, up by 5, up by 7. At this point, you might go, oh, there's no constant change of y. Well, now you look at the next difference. You look to see how much you went from 1 to 3. That's up 2. From 3 to 5, up 2. 5 to 7, up 2. This is what we call your second difference. If your table of values has a constant x change and a consistent second difference of y's, then it is a quadratic. Simple as that. Now, if I look at this table of values as you see it here, and I ask you, hey, is this a quadratic? You can now look at it and know that if there's a constant change of x and a constant double difference in y, it is a quadratic. So if you look at this one, you start off to make sure that you have a constant change of x. From 1 to 2, you went up by 1. 2 to 3, up by 1, and all the way was constant. Now, when you go to check for your y, remember you're looking for constant double difference in y's. To check to see if I have a constant second difference of y's, I would say, well, my first difference, which is plus 3, plus 5, plus 7, and plus 9, doesn't count, because now I want to look to see if the double difference. My double difference means that I have to have,
plus 2.
Oh, look at that, plus 2,
Yes.
plus 2, plus 2. So yes, this is a quadratic because you have a constant change of x and a double difference constant in y. That's how you check for quadratic. So when I'm given a table of values, I could check to see if that's going to make a U by graphing it and looking at it. But sometimes when you graph it, you're only given like a part of a parabola. So it wouldn't even really be very good, because sometimes if I graph something, it might look like this. And I might think that doesn't look like a parabola, but we don't know that it extends this way, right? If they're the only points. So you can't just assume that the only way to check that something is quadratic is by graphing it. And you can't assume that you're going to be able to get the equation. Because if you got the equation and you saw it was a power of 2, then yeah, it's a quadratic. So the other method is to find if there's a change of y that's a double difference and there's a constant in x. The other thing about graphing talks about how to graph quadratics like the good old-fashioned way that we did, good old-fashioned way of plugging x values in, okay? So if I'm given this here, I know that this function, this equation, y equals negative 4x squared, I know that's a quadratic. Why? Because it's got a power of 2. I know it makes a u. Up until you guys learn about all of the things that you discussed at the very beginning that you needed to know to make a parabola, before we learn that, the most basic way of graphing any function is to remember that a function is telling you what y is equal to depending on what x is equal to. So the most basic way is to literally make a table of values, plug in x values, find the corresponding y values, and then plot those points. That's the most basic way of graphing anything. So if I plugged in negative 2, negative 1, 0, 1, and 2 into the graph, into the function y equals negative 4 times x squared, and then I plotted those points, I would be able to figure out what the parabola looks like. So I'm going to go quickly through the mathematics of it. If we plug in negative 2, we know negative 2 squared is 4, and 4 times negative 4 is negative 16. If then I decided to plug in the next value, which is negative 1 squared is 1, times negative 4 is negative 4. Then I would plug in 0, and I would get 0 squared is 0 times negative 4 is 0. Then I would plug in 1. 1 squared is 1 times negative 4 is negative 4. And then 2 squared is 4 times negative 4 is negative 16. Can you recognize anything within the table?
Yes, it's linear.
Do you notice, first of all, we know it's not linear. We know it's quadratic because it's power of 2. But you see that the 0, in this example, I know it's a power of 2, so I know it makes a u. When I look at it, I recognize that at 0, I kind of like become symmetrical. So when I graph this, you could probably make the hypothesis that 0 is that middle line, which we call the axis of symmetry. I plot negative 2 comma negative 16, which is like 11, 12, 13, 14, 15, 16. Negative 2 comma negative 16. I plot negative 1 comma negative 4, 0, 0, 1 negative 4, and 2 negative 16. What can you tell me about the look of this parabola? It's very narrow, isn't it? It's very narrow, and it opens downward. So that's going to lead us to the next thing that I want you to understand, is that the a within the ax squared, all right? So when we have y equals ax squared plus bx plus c, if you're looking at this equation here, you notice there's no bx and there's no c, correct? There's just a. A is going to be very important because A, as you will see when we go through more graphing, if it is positive, it opens up. If it is negative, it opens down. But the next thing that you're going to notice is that taking away the sign, so the absolute value of A, in this case, A is negative 4. So if you just look at 4, the bigger the A, the narrower the graph. And the smaller the absolute value of A, the wider the graph. So visually, if you wanted to have a way of looking at it, you could say that the bigger the A, the narrower the graph. The smaller the A, the wider the graph. So if you had, instead of negative 4, if you had negative 2, you know it would still open down, but because 2 is smaller than 4, it would actually be wider of a U. It would be a wider U. So if A was a fraction, you know that it's a very wide U, as opposed to a whole number. So rule number 1 that you need to know. A doesn't only tell me whether I open up or down. The larger the value of A is, the narrower the graph. It's opposites. And the smaller the value of A, the wider the graph. So with that, let's take that in our heads as we move into the next one. So if I asked you just to look before you graph this, just look at this equation, y equals x squared plus 2. And then look at this equation, y equals negative 3x squared plus 1. Without even graphing it, what can you tell me about the direction of this guy's parabola? It's going to open up. And the bottom one? No. It's going to open down. Now, how about the width? What is A equal to for the first equation? 1. A equals 1. What about the second one? A is equal to negative 3. The negative just told me that I opened down. Who's bigger, 1 or 3? 1. So who's going to be wider?
A.
The wider one is going to be the one that has the smaller value of A. Smaller the A, wider the graph. Larger the A, narrower the graph. So the reason, I'm going to explain it to you, you're going to see that this is actually a rule that you could say, oh, A is 1 for this top one. And for this one, A is negative 3, but the negative is important because it just tells me I open down. 3 is bigger than 1. But the bigger the A, the narrower the graph. If you didn't realize that, let's graph them real quick. Okay, I'm going to go ahead and graph both of these very quickly. So this guy is y equals x squared plus 2. So if I put negative 2 here, that's 4 plus 2 is 6. If I put negative 1, that's 1 plus 2 is 3. 0 is 0 plus 2 is 2. If I put 1, 1 squared is 1 plus 2 is 3. And then it mimics or is symmetrical. I go to the next one. Y is equal to negative 3 times x squared plus 1. So if I do that and I put negative 2 in, negative 2 squared is 4 times negative 3 is negative 12 plus 1 is negative 11. Negative 1 squared is 1 times negative 3 is negative 3 plus 1 is negative 2. 0 squared is 0 times 3 is 0, so that's 1. 1 squared is going to actually become negative 2, and negative 2 and 2 is going to become negative 11. So when I go to graph these, I am going to plot negative 2 comma negative 6, negative 1 comma it's positive 6. I'm going to graph these. I said the wrong thing. Negative 2 comma positive 6. Negative 1 comma positive 3, 0 comma 2, 1, 3, and 2, 6. Now I'm going to try to draw as nice of a U as I could. So here is this one. Now I'm going to graph the next one. Negative 2 comma negative 11 is like down here. Negative 1 comma negative 2, 0 comma 1, 1 negative 2, and 2 negative 11. one was not a very... I'm having a hard time connecting these dots. All right. So with this one, if I'm looking at them, can you see that this bottom one is narrower than that one? Maybe not by a whole lot, but it's definitely narrower than this one. This one is wider than this one is. And the A is smaller in the top, the absolute value. If you look at the top one, it's A is 1, and the bottom one, A absolute value is 3, if we're looking just at the 3 and the 1. So if I was only given these two graphs, and I said, which of these two equations does it belong to, I would know that the top one belongs to the top because it's positive and opens up. And I know that the bottom one belongs to the bottom because it opens down. Okay?
So if you see a negative in front of it.
So again, if A is positive, it opens up. If A is negative, it opens down. The larger the A, the narrower the graph. That's just an additional something that is good to know. Okay? Now let's talk about vertices. When you're looking at these two parabolas, you could tell that there's lots of differences between them and many similarities. The one on the left opens up, so I know that A has to be positive. The value of the A for the B quadratic is opening down, so I know it has to be negative.
Wait, what would be
right?
A?
So I know this one's opening up, so A has to be positive. I know this is opening down, so A is negative. Now, look at the width of these two. Who has the wider
A.
parabola? A. What do you know about the A in reference to this?
It'll be a lower.
It'll be a lower A than this one. So, for example, if this was y equals 2x squared, blah, 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 then this one would be y equals negative, and it would have to be a bigger number. The bigger the A, the narrower. So it would have to be like 4x squared, blah, blah, blah.
Yes.
Right? Or 3 or 2.5, depending on a lot of things. But you know that A, as you look at it, the sign tells you whether you open up or down, and the absolute value of it, without the negative, tells you the bigger the A, the narrower the graph, the smaller the A, the wider the graph. Just an additional something that it's important for you guys to understand with that. Okay, so when you have parabolas, you notice that the vertex of each parabola is like the centerpiece. It's the one right smack in the middle that's going to separate my parabola into two identical halves. That's called symmetrical. Remember that a line that is vertical, a vertical line is what kind of an equation? It is undefined slope, but what is the equation of it? X equals. A vertical line is an x equal to equation. And if you forget, think about this line right there that's going through the vertex. It's a vertical line. Remember, vux, hoi, vertical, undefined, x equals. But if you forgot that, you know it's crossing the x-axis. It's parallel to the y-axis. It's crossing the x-axis at -1, -2, -3. So that means that my x value is equal to -3. If I asked you what is the equation of that vertical line, you could easily go, oh, x equals -3. Why don't you guys tell me what the equation of this guy's axis of symmetry is going to be? Well, I know an axis of symmetry is a vertical line that crosses through the vertex. And I know an axis of symmetry is what kind of an equation? And x equals, and what does x equal? 1, 2. X equals 2. That's my axis of symmetry.
Wait.
So, just without looking at the instructions, all I did was look at my parabola. I identified that a vertex is the middle point that separates it into equal halves. And if you were to put a mirror right smack in the vertex, right in there, that vertical line is an x equal to, and then whatever you cross the x at. Now, when you look at the vertex of letter A, look at the vertex of this one. Is the vertex at the highest point or the lowest point of the parabola?
Lowest.
It's at the lowest point, because the highest points, if you're looking at all my points right there, look at how much higher they keep going infinitely forever, correct? But the minimum point is the lowest point on the parabola. So a minimum is when the vertex is at the bottom of the valley, because it's the lowest point. So what do you think this is going to be called? The maximum, because it's the highest. That leads to the next two steps. The first step is I know that every vertex is what kind of an item? A point. And every point can be written as a?
Equation.
Every point. A coordinate. 2 points, x comma y, an ordered pair. What is the coordinate of that vertex right there, of that minimum? Negative 3, comma 2. That is the vertex of the parabola. Negative 3, comma 2. What is the vertex of the other parabola? 2, x comma y. 2, comma 5. The vertex, which we call the maximum of letter B, because it is the tallest one, it's up in the mountaintop. The maximum is called the vertex, which is a 2, comma 5 location. And this one is called the minimum because it's at the lowest point, and its vertex is negative 3, comma 2. And notice when we go back to the idea of that vertical line that's the axis of symmetry, it's all building on prior knowledge that we talked about. Vertical line, undefined, x equals. This is an x equal to negative 3 equation. And check out x value right there. That means that the x value is equal to negative 3. Duh, x equals negative 3. Look at that, x is negative 3. And the vertex, x equals 2. Oh, look, the x value is equal to 2. Okay, so when you are looking at how to get the vertex of a parabola, but you know what the axis of symmetry is, then you know that the x value is whatever the axis of symmetry is. Because if I am a vertical line that goes through negative 3 at x, if I had an equation that said y equals blah, 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 x squared, blah, blah, x plus 3, all I would need to do is plug negative 3 into x to get the y value, and then I would have the y part of the vertex. Okay, we're going to do a lot of this stuff. Now, so when I'm looking at the parabola, now we're going to talk about domain and range. Let's just look at letter A, please. Just looking at letter A. If I asked you, hey, what is the domain of this function, what letter needs to come to mind? X, because we learned that domain is the x values. So it's asking you, what are the x's that are part of this graph? Well, I know that the arrows at the very top are telling me that I am infinitely getting wider and wider and wider and wider and wider. And when I'm going wider and wider in both directions, that means that my value of x is getting more and more in both directions. So the domain of every quadratic is all real numbers. Because every number, all the way infinitely negative and infinitely positive, would have a location on that parabola. If I picked negative 50, I would have to go way up there, but I would eventually cross through if this infinitely was getting bigger. So when they ask you what is the domain of the quadratic, it's always all reals. The range is a little bit different because the range is telling me what? The y values, correct? I want to know, what are the y's? Well, what can you tell me about the y's that are part of this graph here? It's all of that stuff up there, isn't it? It's from here all the way up. There are no y's underneath this. So, what y value is this vertex at? 2. So the range is going to be that your y's are going to be greater than or equal to 2. because it's 2 or higher. So if I was to look back at this one and I asked you what is the domain again is always all reals because it infinitely goes horizontally. What is the range?
Infinite. Oh no.
Range is the y values. Where are your y's?
Less than or equal to
Yes, it is from 5 and below. So that means your y values are from here all the way down. And that's the way we write y is less than or equal to 5 because it includes 5 because it's a solid point. So it is from 5 and below. That is the range. So y is less than or equal to 5. That's the range. Domain is always all real. X is all reals. So if I had this here, you notice that the vertex is at 2, 1, where 1 is the y value, that it's the lowest. So it's going to be y is greater than or equal to 1. This. The vertex is this point here, which is located at -1, -2, -3, -4, -5, comma, -1, -2, -3. The maximum is -3. That's the maximum height that I get to, correct? And the domain is all reals, always. And the range is going to be that y has to be less than or equal to -3 because it's -3 or everything less.